Hi, everybody. So today is Mechanics Day, or the start of doing mechanics. We're going to go through kind of how to design a mechanical system, specifically precision mechanics, because that's really where you start when you start having to put things in 3D space and expect it to be at some position within a tolerance, some plus or minus, whether it's a quarter of an inch or a tenth of a micron. You have to start understanding that you do things differently than if you just went out and started eyeballing stuff and welding it together. So I'm going to go through a bunch of the components that we use to build mechanics. And the first thing as you're doing any design is to start thinking about static loading and then dynamic loading that might be on something. So I want to talk about that before we get into the actual mechanisms and bearings that support that loading. Because I find that for some reason there's something, I don't know if it's difficult, but maybe it's just something that you got to learn along the way. And so I'm going to teach you about loading a little bit. So first, let's design a little 3D sketch. This is the first step of any design, is I need something that I can actually start to put vector arrows onto and figure out which way the loads are. And so in this concrete mechanism, I tend to draw in kind of broken 3D or isometric 3D. It's usually a hand sketch is good enough, but if it's really quick for you to do something in a computer program, then by all means use that. We're going to need to scale some things, but let's see if we can have an x-axis here. And I think we drew a vertical, some sort of vertical gantry type system on this that has some motion back and forth. So we had some sort of mechanism here that this is the structure itself. Before we actually move it around. Put that back. And I think we had some simple, nothing fancy. That doesn't, this one should have, oops, hello, go away. There. I'm going to redo this. I don't like how that turned out. It needs to be a little bit better than that. So this part here is the part I don't like. So this should be about right here. There we go. I like that. And then we have some sort of structure there. And then across here, we probably have an axis of motion of some sort and a carriage of some sort. We could fill these in here and start to make these some sort of structure that can carry load. Again, this is just broken isometric. I presume you guys can kind of do this. There's nothing with isometric, there's nothing in the world that really looks like this. Because the world has those, vanishing lines but it's super easy to draw 3D this way because all you have to do is draw the front and then you draw some extension lines and you kind of get it. And the only downside is sometimes if you look at it too long, it flips around on you, flips inside out. The drawing does. So here we are, and at some point then we have on this axis here, we probably have some sort of extruder, right? And here comes the concrete out of there, and maybe there's a some sort of pipe that leads over to our concrete pumper. Okay, so the in comes the raw material, comes down the line, and out it goes. And then the idea would be that in general that we're going to build some sort of house that has width and to it, and we'll 3D print this house out of concrete. Kind of cool. So here's say, oh yeah, I want you to design this mechanism now, or specifically what I want you to do is pick mechanisms for, let's see, I would like to do the, you know what, let's just do this axis right here. So let's do this axis here. And a vertical. Let's do a vertical axis. Is it time to do a vertical axis? Yeah, let's do vertical axis. So the vertical axis, I'll draw that. That would be kind of, we'd have some sort of structure over here that would, and same thing on that side. So we'd have, there would be some sort of carriage and attachment point here, carriage and attachment point here. So there would be a drive mechanism making this go vertical. And actually, chances are really good that you're probably going to need to drive it over here and double the load. So as we start to look at the, that's kind of the sketch of what we're trying to do. Does that get us enough to start looking at the static loading? Yeah, a little bit. So let's start to look at some of the static load vectors that would be on this, on the bearing structure. So we start out at the furthest part away from the base, which would be the concrete extruder. We'll start with this section right here. Depending on how you do it, there's going to be some loading on those bearings that carry that back and forth. So let's go to a little bit bigger view of what that might look like, that cross section. So I'm going to draw this a little bit in cross section. Here might be, for instance, the cross sectional, and this would be if you had the, let me see if I can draw this. If we had the vertical piece here and a vertical piece here, this would be this one. And then there's a carriage on this. So this is that piece right there, kind of in cross section. Follow? So we have, and hanging on this is some sort of, I'm just going to draw it out here. This would be the you know, the concrete, maybe the concrete gun or so, because this is where the concrete's coming out down here. So what you need to do is you need to look at this device in a couple of different modes. The first mode we're going to look at is just from static loading. And static loading is pretty easy. In this case, if we start looking at the loads, we have a center of mass here. There's some mass right here. And then there's some forces. Well, what's the force? Well, there's one right here. There's one right here. And the bearings are probably back in this plane right here is the bearing plane. So that means if we're starting to do forces, force due to mass, force due to the carriage, and you start to define these, then they're also acting at some sort of radius or distance away, radius of the carriage, radius of the mass. I'm just randomly assigning variables. I'm not really going to use them right here, but you would start to assign variables as to what are the forces that you're looking at. You may actually say, hey, if this is going to have force coming out of here, well, for every action, there's an equal and opposite reaction. There's probably a force this way due to extruding. Right? If the concrete is going to fly out the bottom, it probably has some lift. It might be negligible. You could decide if it's negligible based on, you know, your general idea of things. So part of what you're looking at here is just what forces in a static world are there. In this case, they're due to gravity. Gravitation, you know, there aren't any external forces other than maybe the concrete extruding. So it's pretty simple. However, the bearings need to be able to handle. In this case, if you looked at the a standard bar, let's say you had some sort of standard stage that had an attachment that was moving back and forth this way. So you're just going to have to live with some of my drawings. You have a carriage. So as we look at the different kinds of load on this and look at moment loading, there's going to be a moment load this way. You guys have had moment loading, right? This would be called the pitch moment, and that would be the moment this way on this bearing. So it'd be like the bearing doing a wheelie, right? Back and forth. You would have a roll moment that would be like in this direction. So these bearings may or may not have some roll moment side to side. And then what's the last one that you would have? Pitch, roll. There's three.
Yaw.
Yaw, right. And so yaw is the skewing. That's like what happens when you get out on ice and you start to get sideways. You've got a yaw motion. And so yaw would be, you know, this axis moving in this direction. So if you look back on this diagram now, and you start to look at, let's look at this force right here. Let's look at the main one. Let's look the force due to the mass that this has to hold. There's a moment. The moment in this, on this particular bearing set that's in here, somewhere somewhere down buried in here are some, I'll just draw them simply, there's some linear bearings in there. So the actual force on those, the moment due to the mass on this would be what kind of moment? What would it be, yaw, pitch, or roll from gravity acting on this? Nobody guessing?
Roll.
Roll, right on. Yeah, so in this case, you have a roll moment. And that roll moment is, in its simplified form, is just F sub m times R sub m, right? Force times distance gives you a moment. And that moment then would be newton meters, foot pounds, inch pounds, some sort of torque. It's putting a torque on this. And what you would do then, if you've selected a particular mechanism, then, and has a part number, and you say, okay, let's go back, this IKO device here, this is going to be the mechanism here, and you would actually go look up for this set of mechanics, how much moment in the roll direction can this bearing have? So for instance, this bearing might not be able to handle it might handle force this direction, it might handle force this direction, and it might have a moment. Keep in mind that this, if you do the free body diagram, this part here, let me highlight it, the body of the actual unit itself is seeing a force, there's a force on it deflecting it, so that it's going to deflect a little bit. And so part of what you're looking for is, do you have enough force, enough structure in the body of this that when you load it, it can handle the load? And then do the bearings actually handle the load that you're attaching to it? So you got a couple different things to think about. This one right here, I'm not so worried that you work on that one. That's more of a structures and maybe 340, and I don't know, you've taken some other classes, deflection of that. And it's almost something the manufacturer has to give you if you plan to load that. Typically, when you choose mechanics, so you can see on here, there's a mounting hole pattern that's in here. And typically you wouldn't have this thing that's housing the bearing be the actual support. You would mount this to some other structural member, right? So they would be mounted to it. So the green thing I just drew is supporting the main deflection from just the overall mass of the unit. And so all these bearings have to do, they're going to travel a straighter distance, and they got to worry about the moment loading. So as you start to look at choosing, you very seldom wouldn't have very many, you'd have, let me put it this way, you would only have one or two of the moments in static, and then when you start to move things around, they change to a different moment. For instance, as we drew this static, it simply is the force times the distance, and this force is really just, you know, this is mg, right? Pretty simple. But as you start to move it, things change a little bit. What happens when you start to accelerate this? I need more colors actually. So let's say we start to add acceleration in this direction. We're going to start moving it back and forth along its travel. As soon as you accelerate it, because we know that the motion profile has some acceleration and deceleration to it, as soon as you accelerate it, now instead of g, now we have a. So you have a different acceleration. So static typically means what happens due to g. Then the dynamic loading, you say, what happens when I start to accelerate it? Well, where do you get your acceleration number from in the first place? Well, from your motion profile. How fast do you want this thing to go, and how quickly do you want to get it up to speed? So we would need some numbers for that. And from there, you would quickly calculate what's the acceleration rate, and then you have a number that you can put in there. So for the acceleration. So, but what happens to the moment loading of this device, and what new loads are created when you accelerate it that way? This mass is still out here. Instead of roll moment on that bearing, what kind of moment would you have due to accelerating it along its axis?
Yeah.
Depends, right? This now, if I drew the center of mass right here. And if the center of mass is right here, when you begin to accelerate it, I don't think you have much yaw. You have mostly pitch moment. And again, so when you're designing along, there's some amount of engineering and some amount of estimation and some amount of ignoring the minutia. And so what I'm really trying to do when you're doing this is not a complete exhaustive calculation. It's pick the biggest ones and make sure you're checking those. And generally, if you've got a bearing that can handle the biggest one or two moments or forces, it's going to handle the minutia ones too. And so you really don't need to deal with them. Some of that's judgment and experience. In this case, I would say as we accelerate this, if the mass up here is center mass is on this axis right down the center, then you have a pitch moment. If though you decide, no, the center mass is actually down here, and now you're accelerating this direction, now all of a sudden you have both pitch and you have some, in this case, it'd be yaw, right? Because this would tend to have a yaw motion. And so this bearing here would begin to see a yaw moment. And what do you do with that? You do a quick calculation. How big is it? And it's the same thing. It's, well, what's the force due to acceleration? And what's the distance it's acting on? So in this case, you'd have this R would now be your new distance to look at the yaw moment. Where is the center of mass below the axes? And then how much is it accelerating along here? What's A? And so F is center mass MA times R, and you have a yaw moment. They're really the calculations are that easy for the most part. And then you go look up and you say, okay, on this stage, the yaw moment it can handle is 14 Newton meters. And I calculated it's 4 Newton meters needed. Okay, good. 14, 4, therefore I have a safety factor of 3.5, right? Because remember I say when we're dealing with the electrical part of things, do I need to draw that out for you guys? Did you get what I mean by those numbers? Did I go too fast on that?
Can you draw it out, please?
Yeah. Okay. So, so in this axis, we would say, let's just keep going on. We would say the moment due to yaw on this would be the force, the force which comes from the mass times acceleration times, and we'll give it a label. Let's give this R sub D for how far it drops. I don't know. So times R sub D would give you the moment on there. MA times RD gives you a moment. Let's say you came out and said, that's 4 Newton meters, for instance. Then what you do is you go to the mechanism that you've chosen. He's like, I chose this guy, or a larger version of this, and you would go look up the yaw moment of this device, of this actual model number. It's one of the places where you start to need to get away from distributors and get to manufacturers, so that you can look up the yaw moment, the yaw moment would be the twisting moment on this, or the twisting moment this direction on that. That would be yaw. Pitch would be this direction. Roll would mean this direction. This works pretty good. And then yaw is this way, right? So in this case, since it's like this, and we have the mass down here, it's creating a yaw moment on this bearing. Make sense? So we go look up how much, we know that it's going to be 4 Newton meters, and then you go look up and say, oh, this one can handle 14, so therefore your factor of safety is 14 over 4, which is about 3.5. And so check. This is the kind of calculation you need to do. It's very similar in my mind when you flip to the electrical side. I always said draw the circuit, find the switch, the load, the power supply, and then make sure you're limiting the current, you're doing all this stuff, and then finally you're done when you say I equals, and you say, oh, I equals some number on the electrical side. On the mechanical side, you're kind of done when you got to a factor of safety for that particular number that you thought was the important one to calculate. Generally, you're going to have at least 1 or 2 moments to calculate. Some examples, if you just had, I'm going to switch pages now. So you got the idea then. So when you're doing loading calculations, it's did you get to a factor of safety? On some of the other stuff like couplers and drives and motors, it's did you get to a part number, and then what's maybe the factor of safety on your torque, so to speak. Okay. So let's deal a little bit with non-moment loads. Let me go to the next page. So in this diagram, I'll just kind of put it back up here real quick. So we've got this gantry type device with a cross axis to it. One of there's 2 different kinds of loads that you would look up on a stage. some of the loads are moments and some are just forces. For instance, this one down here, I'm not actually asking you to look at it, but that axis, if I drew it, let's draw it like this. Here's the axis. We had the vertical part coming off of it. You had some sort of carriage down here, and then there were some structural members. And then maybe over here was the motor driving it back and forth. So this actually ended up moving this direction, back and forth. So let's look at this one and see what loads come to play if you're calculating the bearings that are down in here. You know, somewhere down in here is the bearings that are is moving back and forth, that's supporting the load. When it's just static and it's just sitting there, let's look at, well, we have, this has, you know, here's M, again, mass of the, I don't know, what gantry, we'll call it. You get to design whatever labels you want. The key is to, you know, do it so that you can actually define the label and then you use them in the equations and you're not reusing the same one over and over, hopefully. So we'll just say there's the mass, and that creates then a force due to the mass, and it's, you know, M sub G times G. Pretty simple on that one. When you look at this bearing, when it's just sitting there static, there's not a moment, it's just a plain force, and the force is, you know, in that direction. So in this case, you would go grab your mechanics, and it would look like this. Here's the motor end, where the motor attaches. And if I move over here, let me move this over into the picture a little bit. Here's the carriage. The gantry might be sitting right here. And so it puts a direct force right down on it. Statically, it's just got to carry the load. Can the bearing handle that? So you actually go look up and say, okay, how much can this bearing handle in this direction? And it's got, it'll give you 3 different loads. In this case, well, actually 2. It'll give you side load, which is, you know, if you'd had it mounted, instead of mounting the bearing this way, if you have the bearing mounted this way, then it might see a side load. If you have the bearing mounted this way, it's going to see a direct top load. And then you would go look to the manufacturer specs, see what they call it, and compare and see if this, you know, if this holds the load. That's static. Now, when you start to move this thing back and forth, as soon as you start to say, you know, let's give it A, now what kind of loading does this bearing block right here see? Now what kind of loading would this bearing block see as soon as you give it A? It would start to have a load this way, right? And that would be a pitch moment. And you would have to kind of say, all right, where is this center of mass? You know, what's the moment? What's the radius? These are a lot of times on this, you don't know the exact answer. So what you do is you take the worst case. Worst case would be, in this case, would be when you have it, this cross axis and the extruder, when they're way up at the top, that puts the mass way up there. Now this force is larger. The mass is way up here, so the radius got larger. So therefore, the pitch moment on this bearing down here is going to be worst when you move the load to the very top. This is where some robotic manufacturers, actually some machine manufacturers, you can solve things in programming, actually. You could say, no, we're never going to allow this axis here to move at that acceleration when the load is way up there. if we want to do, we'll always move the load down here. Then we'll accelerate back and forth, and then we'll allow it to go back up. It'd be like if you had a robot arm and it's moving around, its worst inertia is when it's fully extended. And sometimes you would say, no, I don't ever want to do this move here, back and forth. What I'll do is I'll move from here, I'll come in, lower the inertia, then move, and then go back out. And it creates a lot less torque on this axis right here. Doing this motion is tough, and it might require a lot of torque out of your motor. But if you did this motion, it takes a lot less torque out of this axis. And you have control over that in your programming. See what I mean? So, but you could just say, you know what, worst case is it's doing this, or worst case is its R is way up here. And so then you would, the moment of pitch would be MA times R. In this case, it'd be mg times the acceleration rate times r t. We'll call it r sub t. And then again, you'd look up what the manufacturer says it's capable of, that bearing set, compare that to what you're doing, and you'd get a factor of safety for that axis. So every single axis that you dream up or draw is going to have a different set of things that you're going to need to, there's not one universal, here's how you do it. You have to look at the sketch and start to think about each axis, and when you put that axis in motion, what kind of forces does it have and what kind of moments does it have? And you have static ones and you have dynamic ones. Static from regular G, dynamic comes from the acceleration profile that you plan to put on it.